Welcome to this explainer. Today, we're diving into the totally fascinating, kind of mind-bending world of topology. We're going to explore this incredible subject using a really brilliant, authentic set of handwritten mathematical notes. We're going to completely decode the fabric of mathematical spaces, looking at what actually happens when the normal rules of geometry are just left behind. So get ready because we're about to seriously stretch our imaginations. But before we get into the heavy lifting, let's talk about what a topological space actually is. Think of classical geometry as this world of rigid steel, right? Shapes have exact lengths, precise angles, fixed distances. Well, topology is entirely different. It's all about stripping away that rigid geometry to see what fundamental properties actually remain. When a space is stretched, twisted, or bent, it's kind of like geometry made of rubber. Distance becomes just a suggestion, and the real question is simply, how are things connected? So here's our roadmap for today. First, bending space with quotient maps. Second, defining connected spaces. Third, unions, images, and products. Fourth, the path to connectedness. And finally, visualizing path connectedness. All right, section 1, bending space, quotient maps. Let's get right into it and talk about how we can mathematically collapse space using something called a quotient map. This is honestly where topology gets really fun, because we're actively taking a large space and just squashing it down into something entirely new. The notes we're exploring define this specific, really cool map. Imagine curves, parabolas opening to the left. The math here dictates that every single point on one of those parabolas belongs to the exact same equivalence class. So the quotient map literally collapses that entire infinite parabola down into a single point on the real number line. It's basically taking an infinitely tall curved 2D space and folding it perfectly flat into a 1D line. How wild is that? Now, this actually brings up a huge trap in topology. When we have a tool that works well, like a quotient map, which is continuous and hits every point in the target space, we tend to just assume it behaves predictably, right? You might intuitively think, hey, taking two well-behaved quotient maps and multiplying them together obviously gives me another perfect quotient map. But as our source material explicitly warns us, reality is way trickier. The product topology of two quotient maps doesn't have to be a quotient map at all. It's a really stark reminder that in topology, you absolutely cannot rely just on intuition. Moving right along to section 2, defining connected spaces. Let's clear the board a bit and define our next core concept. What does it actually mean for a space to be a single, unbroken piece? Well, in topology, we usually define connectedness by defining what it isn't. Think of a separation. A space is disconnected if you can slice it into two completely separate, non-empty, non-overlapping open sets. If you can draw a rigid boundary that perfectly partitions the space into two disconnected blobs, boom, it's separated. Therefore, a space is only connected if you absolutely fundamentally cannot do this. It has to be impossible to slice it apart without breaking the mathematical rules. And here's the crazy thing. Connectedness is completely relative. Take the set of real numbers. Under the usual topology, the real number line is connected, just like you'd expect. But if we apply a discrete topology or a lower limit topology, that exact same number line completely shatters into disconnected pieces. The numbers themselves didn't change at all. The mathematical lens we use to look at them did. All right, section 3, unions, images, and products. So now that we know what a connected space is, how do we build new ones out of old ones? The handwritten notes give us what is essentially a topological construction kit via 4 massive theorems. They prove that as long as we combined connected spaces using certain safe methods, that connectedness survives. For example, if you have a bunch of connected spaces and they all share just one single common point, kind of like petals on a flower, their union is connected. If you push a connected space through a continuous map, the output is connected. And, super importantly, if you take a finite Cartesian product of connected spaces, it remains connected. But hold on, that word finite in that last rule is absolutely crucial. Multiplying 2 or 3 spaces together, totally fine, it preserves the connection. But if you push the limit and try an infinite Cartesian product using something called the box topology, the whole system just breaks down. The notes actually lay out a proof showing a clear separation between bounded and unbounded sequences here. By moving from finite to infinite dimensions under the specific topology, the previously unified space fractures entirely and becomes completely disconnected. Which brings us to section 4, the path to connectedness. This shifts our perspective a bit to a much more physical way of thinking about how points in a space relate to one another. We just established what it means for a whole space to be considered one single piece. But what if we zoom in? What if we just want to travel from a starting point A to a destination point B without ever stepping out into the void outside the space? This is where a concept known as path connectedness comes in. Instead of dealing with abstract open sets, imagine mapping an interval of time, say from time A to time B, directly into our space. The function basically takes that timeline and draws a continuous curve. At the start of the interval, you're at point X. At the end, you're at point Y. If you can draw this continuous path between absolutely any 2 points in the space, then the space is path connected. Let's make this concrete in Section 5, Visualizing Path Connectedness. So let's ground this with a classic example pulled straight from our source material, the unit ball. In any dimension, this is just defined as every point that's a distance of 1 or less from the center. It's a solid sphere, right? To mathematically prove this space is path connected, we don't need to overcomplicate it. We just need to definitively show that any 2 random points inside this ball can be connected by a path that never, ever crosses the outer boundary. And there's an incredibly elegant algebraic proof for this. You just take 2 points, let's call them x and y. You define a continuous function based on time t, ranging from 0 to 1. The formula is beautifully simple. F of t equals 1 minus tx plus ty. When t is 0, the y cancels out and you're precisely at point x. When t is 1, the x cancels out, leaving you exactly at point y. For any fraction of time in between, you're somewhere on a perfectly straight line between them. Basic inequalities then prove the length of this path never exceeds 1, meaning your mathematical journey never accidentally steps outside the solid sphere. And we can take this a step further. We just proved the solid ball is path connected. But what about the hollow surface, the unit sphere itself? Well, there's a brilliant trick for that. By taking a punctured Euclidean space, which is basically everything except the exact center point, and applying a continuous normalization map, we can project it. This map takes any vector and stretches or shrinks it so its length is exactly 1. It acts almost like a mold, pushing every point in space firmly onto the surface of the hollow sphere. Because the continuous image of a path-connected space is itself path-connected, we've just formally proven the unit sphere is connected. Ultimately, that's the real beauty of topology. We started out today looking at ways to violently collapse parabolas into single points, and we ended up charting completely unbreakable mathematical paths across multidimensional spheres. It forces us to strip away the distractions of rigid measurements and shapes, and I think it leaves us with a pretty massive, provocative question. If we can bend space itself and redefine what distance even means, what are the invisible, fundamental mathematical threads that truly hold our universe together?